Welcome to the quantum realm, where things aren't as they seem. Here, the rules of the game are different, the players elusive, and the outcomes are often stranger than the wildest of imaginations. We're stepping into a world where particles can exist in multiple places at once, where they can spin in two directions simultaneously, and where observing a phenomenon can fundamentally alter its state. This is the world where the famous or infamous Schrödinger's cat dwells. A world that, despite its oddities, underlies the reality we experience every day. From the glow of distant stars to the intricate workings of our own cells, quantum mechanics plays a crucial role. And at the heart of this quantum world lies a paradox, a riddle wrapped in an enigma, a cat in a box. Today we're unraveling the mystery of Schrödinger's cat, a paradox that has puzzled minds and sparked debates. In 1935, physicist Erwin Schrödinger proposed a thought experiment that shook the foundations of quantum mechanics. This thought experiment, known as Schrödinger's cat, was a way for him to illustrate the strangeness of quantum mechanics and the concept of superposition. Let's imagine a scenario. Picture a box. Inside this box, we have a cat. Along with the cat, we also have a flask of poison and a single radioactive atom. Now, the fate of our feline friend is intricately linked to the state of that atom. This is where things get interesting. If that atom decays, it triggers a mechanism that breaks the flask, releasing the poison and, unfortunately, causing our cat to meet its demise. However, if the atom doesn't decay, the poison stays contained and the cat remains alive and well. So far, so good, right? Here's where we enter the realm of quantum weirdness. According to quantum mechanics, until we open the box and observe what's inside, we cannot say for certain whether the atom has decayed or not. And since the cat's fate is tied to the atom, we also cannot say whether the cat is alive or dead. Now, hold on to your hats, because this is where it gets really mind-boggling. According to the theory, until observed, the atom is in a state of superposition. It is both decayed and not decayed at the same time. And following that logic, the cat, too, is both alive and dead at the same time. Only when we open the box and observe what's inside does the superposition collapse into one state or the other. The atom is either decayed or not decayed. The cat is either alive or dead. The fate of our feline friend is linked to the atom. If the atom decays, the poison is released and the cat meets its demise. If not, the cat lives. And that, my friends, is the perplexing paradox of Schrödinger's cat. According to the Copenhagen interpretation of quantum mechanics, until we open the box and observe, the cat is both alive and dead, existing in a state of superposition. Now, the term superposition might sound like something right out of a superhero comic, but in reality, it's a fundamental concept in quantum mechanics. It's the idea that a particle can be in multiple states at once, each with its own probability. It's only when we decide to take a peek that the superposition collapses into a single definite state. Applying this to Schrödinger's cat, the feline is neither alive nor dead until we open the box. It's in a superposition of both states. In this thought experiment, Schrödinger was trying to highlight the strangeness of quantum mechanics when applied to everyday objects. But let's take a step back. The concept of superposition is not as alien as it sounds. Think about flipping a coin. Until it lands, it's in a superposition of both heads and tails. It's only when it lands that it collapses into one state. However, the difference between a coin flip and a quantum particle is that the latter can actually be in multiple states at once. This is not just a limitation of our knowledge or a lack of information, it's a fundamental aspect of the quantum world. So if we apply this to our feline friend in the box, it's not that we don't know whether the cat is alive or dead until we look. It's that the cat is truly in a superposition of being both alive and dead at the same time. This concept of superposition is what makes quantum mechanics so fascinating, but also so counterintuitive. It challenges our everyday experiences and forces us to rethink our understanding of reality. This seems absurd, right? How can something be in two opposite states simultaneously? Well, that's the enigma of quantum superposition. So, as we continue to explore the quantum realm, remember to keep an open mind. After all, in this world, a cat can be both alive and dead, until, of course, you decide to open the box. When we finally peek inside, the superposition collapses, and the cat is either alive or not. But when exactly does this transition happen? That's the million-dollar question. This million-dollar question brings us to the role of observation in quantum mechanics. In the classical world, observing something doesn't change its state. You can look at a car, a tree, or a sandwich, and they remain just as they were. But in the quantum realm, things are different. Observation becomes an active participant, and the act of looking can dramatically change the state of affairs. This is the crux of the Copenhagen interpretation, the most widely accepted interpretation of quantum mechanics. It suggests that the act of observation collapses the wave function, the mathematical description of all possible states of a quantum system, into a single, definite state. In the case of Schrödinger's cat, the act of opening the box and observing collapses the cat from being both alive and dead to being definitely one or the other. But this interpretation raises another question. What constitutes an observation? Does it require a conscious observer like a human, or could it be an inanimate measurement device? And if it's the latter, where do we draw the line? Does the very air in the box count as an observer since it interacts with the cat? These questions highlight the measurement problem, a deep and unresolved issue in quantum mechanics. Although quantum theory has been incredibly successful in predicting experimental results, how it relates to the reality we experience remains a mystery. It's a mystery that physicists have been wrestling with for nearly a century, and it's a mystery that's at the heart of the Schrödinger's cat paradox. Schrödinger's cat isn't just a quirky tale. It challenges our understanding of reality and observation. It forces us to question the nature of the reality we experience and the role we play in it. So, as we journey through the quantum realm, let's keep these questions in mind. After all, the mysteries of the universe often lie where we least expect them. It asks us to consider the line between the quantum world and the classical world we see. Welcome to the divide, the boundary that separates the subatomic from our everyday reality. It's a line that Schrödinger's cat paradox forces us to ponder. The quantum world and the classical world, though seemingly disparate, are intricately intertwined, and understanding this dichotomy is crucial to deciphering the mysteries of our universe. In the quantum realm, particles exist in multiple states at once, a phenomenon known as superposition. It's a world where time is irrelevant and realities are innumerable. On the other hand, the classical world, our world, is a place of singular realities. The chair you're sitting on is just a chair, not a flurry of probabilities. But where does one world end and the other begin? Schrödinger's cat offers a window into this conundrum. The cat in the box, simultaneously alive and dead, is a creature of the quantum world. Yet, when we open the box, it suddenly adheres to the classical world's rules. It's either alive or it's not. The act of observing, it seems, forces the quantum world to choose a reality. But is it really that simple? Some physicists propose that both worlds exist in parallel, with the quantum world giving rise to the classical one. Others suggest that the divide is not as clear-cut, and that quantum effects can spill over into our macroscopic world. Yet, the question remains, how does the universe decide when to switch from quantum to classical rules? This is the essence of the quantum classical divide, a concept that continues to perplex and fascinate scientists. It's a riddle that lies at the heart of our understanding of the universe, a paradox that challenges our perception of reality. So, what do you think? Is the cat alive, dead, or both? The answer might just lie in the eye of the beholder.